Hi, everybody. Thank you very much for coming. My name is Rahul Pathak. I'm the Senior Product Manager for Amazon Redshift. And with me today, I've got Jay Lee, who's in data infrastructure at Pinterest, who'll be talking about their analytics platform and how they've been able to leverage Redshift. Before I get into this, just a quick show of hands. How many of you are familiar with or using Hadoop or HDFS? OK, about a third. And how many of you know about or are using Redshift? All right. Well, for about a third of you, a lot of what I'm going to cover is going to be somewhat elementary, but hopefully Jay can get into some details so that you'll learn some new things. For the rest of you, if there's one thing I'd like you to remember from today, it's that Redshift is a fast, relational data warehouse that's easy to use, costs less than $1,000 per terabyte per year, and lets you scale from 160 gigs at the low end to over a petabyte, 1.6 petabytes of compressed data at the high end. And Redshift is part of AWS's big data platform. And so I think AWS has really got a great set of atomic building blocks to allow you to compose applications using tools that are targeted at specific use cases. And so for data collection, we have fast ingestion into S3, for example. You can use Direct Connect, which is dedicated 1 gig or 10 gig E lines that you can use to batch your data centers to ours, and you can lease multiple of these by the hour. We've got DynamoDB for low latency structured data collection. It's essentially a very scalable, very high throughput, very low latency NoSQL store. Customers use this for perhaps voting applications that are real-time, high concurrency. We've got Kinesis, which is one of our newer services for real-time streaming. This allows you to really throw as much data as you can generate, as fast as you can generate it, at a durable stream that you can then consume and route that data into other areas for processing or analytics. When it comes to storage, S3 and Glacier are two of our well-known services in this area. S3 is an object store, put whatever you want on it. And it's sort of the Chicago O'Hare of AWS. Every other service within AWS can talk to it. So if your data's on there, it can be pulled into any of these other services. And Glacier is really for cold storage. So if you've got data en route to somewhere else but want to keep a copy for compliance or in case you might ever need it in the future, Glacier is your service for that. And on the analytics side, there's Amazon Elastic MapReduce, or EMR. This is our managed Hadoop environment where you can spin up or spin down clusters to access and do your MapReduce jobs. Or Hive workloads, and Jay will be talking a little bit about how they're using MapReduce, although not EMR at Pinterest. And we've got Redshift, which is the focus of today, a relational data warehouse designed for SQL-based access to large data sets. And then you can obviously run any arbitrary application that you can conceive of on EC2. So with Redshift, our goals were really fairly straightforward to state. We wanted to be 10 times faster than traditional row-based systems for analytic queries. We wanted to be 1/10 the cost of Columnar systems that were out there, and we wanted to be easy to use. And this service really came into being because our customers wanted data warehousing done the AWS way. So easy to provision, pay by the hour, the ability to scale as they went. And then for us, another goal was to make sure that Redshift was compatible with the tools that customers already use, and that means SQL. Now, by making Redshift something that you can provision by the hour rather than something that requires 3 months of negotiations and then 3 months of deployment, we've really expanded the number of use cases that customers can use Redshift for. And so you've got enterprise customers who are using Redshift to either extend their existing data warehouses, they're bringing in new workloads when they're running out of capacity, or you have them migrating completely from their traditional systems into Redshift because they're able to get real benefits in terms of time to market for the business as well as significantly lower costs. So Redshift, for example, you could provision 100 terabytes in under 3 minutes and get that up and running and have a SQL endpoint that you can start to use. On the big data side, we're seeing a lot of companies that weren't traditionally using data warehousing begin to look at Redshift. Pinterest is one of those. And here it's about combining multiple forms of data. Typically, we see log data from event loggers or web servers or mobile devices being combined with transactional data and then being brought into Redshift for SQL analytics. And Jay will talk in a fair amount of detail about what they've done at Pinterest in this area. And on the third major area that we've seen is SaaS companies that provide analytics to their end customers. So think of an email targeting platform like StrongView. They provide reports and analytics that their end customers consume about campaigns. They've been able to put Redshift behind the scenes and so see gains in performance, cost, and the ability to scale as their businesses grow. Here's just a few customers that have been using Redshift in production. You'll hear from Jay on Pinterest's use case. I think the main things to take away here are really that notion of performance, price, and ease of use have opened up Redshift to a range of customers, range of sizes from startups to large enterprises like NASDAQ, as well as a range of vertical segments, social, mobile, gaming, financial services, healthcare, and a global customer base in the US, Europe, Japan, and Asia Pacific. And so we're always delighted when customers are able to share with us and others how they've been using Redshift, and you can find out about these and others on our website and on the web in general. Another part of a data warehouse is that it doesn't exist in isolation. It's part of an ecosystem of tools that customers are typically familiar with. And we've been very excited as well to see a rapidly growing ecosystem of partners around Redshift. And so if you're looking for help with projects, or you have BI tools or data integration tools and platforms that you already use today, you can use them with Redshift. And because Redshift essentially speaks Postgres over the wire, if you have a tool that speaks to a Postgres database, it should work unless it's doing some real low-level admin functions within Postgres that aren't supported, and we lay out what those are. And a number of our partners are here today in the booth, so definitely drop by and say hello to them if you're interested in what they're doing. And on the AWS Marketplace, which is really an app store for AWS where you can, with a click, just provision software and use it, there's also a special Redshift section, a specific Redshift section where you can get software for data integration or BI or analytics, provision it with a few clicks, start using it, and tear it down when you don't need it. One other question that customers often have is, great, I've got a 100 terabyte data warehouse, how do I get data into it? And no data is ever born in a data warehouse. It always moves there from some other system. And so as long as you can get data to S3 at any rate that saturates your outbound connectivity, you can get data into Redshift at pretty high velocity. And so parallel loading to S3 is an option. Direct Connect we mentioned briefly. If you're shipping a petabyte of data, FedEx can be surprisingly high bandwidth, and so import-export lets you ship us drives, and we'll get that data onto S3 and get your drives back to you. And then you also have help that you can get from systems integrators, consultants, as well as our data integration software partners, a number of whom are here today, and SnapLogic announced a free trial for their connector to Redshift, so you can definitely have some options for easy experimentation. And then on the consulting side, again, folks all over the world that can help you with your projects. So just to dig in a little bit to Redshift architecture, it's designed to be run as a clustered system, although we do make a single node variant available for ease of use and smaller data set sizes. But Redshift has a leader node, which is where you connect your SQL applications to. You use JDBC and ODBC drivers. They're Postgres drivers from the Postgres website. And the leader node just contains metadata about all the data in the system, and it's responsible for coordinating query execution. The compute nodes in the cluster are connected to each other and to the leader node using our 10 gigabit non-blocking high-performance networking. And this is where your data is stored and where all your processing takes place. And so when you issue a query, we'll actually run it in parallel on all of the compute nodes at the same time, and then bring those results back to the leader node into your application. We use local storage for performance, and those of you familiar with EC2, you'll know that local instance storage is ephemeral, and so Redshift takes care of replication automatically and takes care of continuous backup to S3. So you get the benefits of local storage for performance and managed storage for durability, and we'll talk about some of those features and how they work in just a second. And we try and do as many operations in parallel on the compute nodes as we can. So it's query execution, it's loading, it's backup, and I'll go into detail in all of these in just a second. And then Redshift runs on a hardware platform that's optimized for data processing. And so we have two of these. One's a hard disk-based platform. This scales from 2 terabytes at the single node level to 1.6 petabytes, and this is compressed data, so our customers typically see 4 to 8x compression coming from other databases, so you can fit a ton of data into a single Redshift cluster. And then we also recently announced in late January our SSD-based platform, and this lets you do two things. It lets you start smaller. The single node here is 160 gigs compressed, and it lets you scale to 256 terabytes of SSD, which gives you a ton of performance if you're primarily performance-driven on the cluster side. And here's a bit more detail on the node types. You can see we've got two families. The DW1 is our magnetic platform, and they come in two sizes. The extra large has 16 gigs of RAM, 2 cores, and 2 terabytes of compressed storage across 3 magnetic spindles dedicated to that node. And then the creatively named 8 extra large is 8 times the size, with 128 gigs of RAM and 16T compressed per node. Now, this is really optimized for use cases where storage costs are paramount. So it's a high-performance system, but it's really designed for the lowest cost platform that we offer. And this is $1,000 per terabyte per year when you're using our 3-year reserve models. And as I mentioned, you can scale from a single extra large node to 100 of the 8 extra largest nodes. And I'll explain how Resize works, but it's a push-button operation. And then the SSD node types, here we have a large. And this starts, again, same amount of RAM as the extra large on the DW1. It's 16 gigs of RAM, 2 virtual cores. This is Intel Ivy Bridge, and it's 160 gigs of compressed SSD storage. And the 8 extra large here is 16 times bigger than our large, and this has 256 gigs of RAM, 32 cores, and 2.56 Ts of SSDs. And if you're running 100 of these in a cluster, that cluster would have 24 terabytes of RAM, 3,200 Ivy Bridge cores, and hundreds of terabytes of SSD, so it's a beast. And if you look at the price points, this is really designed for two things. One is if you have less than 500 gigabytes of data, actually running 3 of the SSD nodes will be cheaper for you than running a single magnetic node. And the reason is that that single large node of SSD starts at 25 cents an hour. And so you can run 3 of them for 75 cents versus the single node magnetic, which is 85 cents an hour, but gives you 2 T of storage. And then it's also designed for really performance-sensitive workloads where you want the benefits of SSDs and you want lots of memory and CPU per unit storage on a given node. And because Redshift is a clustered system, you can just add nodes to your cluster to get more performance as well as to add storage. And if you look at the pricing on a per terabyte basis, what you'll see is that for an equivalent size, so a terabyte of SSD will cost about 5.5 times as much as a terabyte of magnetic, but you'll get about 10 to 15 times the query performance out of the SSDs. And so the price-performance equation is a very favorable one for our customers, and it's really a function of what kind of workload you want to run. And you can switch between cluster sizes anytime. Again, our resize function allows you to change node types. So when we talk about being 10 times faster, we really want to be, performance is a big, big emphasis for the Redshift team. And performance at scale is really about being efficient with I/O. And so with Redshift, it's a columnar system. And so what this means is that when you define a table, Redshift will automatically store each column independently. And the reason this is useful is that if you think about your typical analytic queries, you're looking at a subset of the columns in a database. And so, for example, in this situation, I'm sorry, it's hard to read, but if you were trying to get the total amount in a row-based system, you would read all of your data, and then you would throw away 3/4 of it in this example because you don't need it, it's not relevant. Whereas in a column store, you just read the column that you care about because each column is independently stored. And so in this case, you save yourselves 75% of the I/O just to respond to that query. And so columnar systems are inherently more efficient with I/O for analytic queries. Another big benefit of columnar storage is columnar data compression. And because each column, which typically contains relatively homogeneous data, is stored independently, Redshift can actually analyze it and pick the best compression scheme for each column automatically. So when you load data into a Redshift cluster, we actually sample your data for you and then pick a compression encoding for each column and then use that going forward. So what you're looking at here is the output of an analyzed compression on a table. You can see that it's made choices per column. You always have the ability to override these and specify your own, but by default, Redshift will sample on the first load into a column, into a table, and pick an encoding, and then run with it from there. And as I mentioned, compression, typically our customers see anywhere from 4 to 8x. Naturally, some columns will compress much, much better than others. If you have a list of dates or stock ticker symbols or stock prices, you'll see much more than 4 to 8x. But with real-world data sets, 4 to 8x is what our customers see. And the big benefits are, one is query performance. With any given read, each block gets back 4 times as much relevant data. And the other big benefit is cost. You need a much smaller cluster to house your data sets, and that's a direct benefit from the customer perspective. Another technique that Redshift uses is zone maps, and these come into play with sorted columns. If you think about a very common use case for Redshift is bringing event data. So you've got people looking at your website, you're bringing event data into Redshift. That data unfolds forward in time, for the most part. And when you load that data into Redshift, if you sort based on time, Redshift can build a zone map of your table and keep track of the minimum and maximum values in any given block. And then if you have a date range in your where clause, which is very common, again, with event data, because you typically care about what happened in the last hour or the last day or the last month, we can skip the blocks that aren't relevant. And again, this theme of being efficient with I/O, not reading unless you really have to, is what we're trying to accomplish here. Direct-attached storage, as I mentioned, it's really about performance. We want to maximize the scan rates between the drives and the CPUs on the nodes. We publish these on our website, but if you look at our magnetic platform, the DW1, that can deliver 2.4 gigabytes per second of scan rate per 8 extra large node. And that goes up linearly with the number of nodes in your cluster since we're executing queries in parallel. And on the SSD platform, you actually get 3.7 gigabytes per second of scan rate. So these are the 8 extra larges. The smaller node sizes will be essentially the fraction of those. But again, linear gains as you add nodes. And one of the things that we do here is anytime there's a write to a Redshift cluster, it's not acknowledged until that data is actually in 2 places. And so we replicate data automatically behind the scenes from one set of drives onto a set of drives on different nodes in the cluster. That allows us to transparently deal with drive failures. And the goal, and this doesn't count against your storage limit per node. So when we say 16T, that's 16T of data for you. We reserve an extra 32 on those nodes that we use for replication and for temporary spills. And if drives failed, we'll rebuild mirror copies on that additional spare space. So that's not something that you pay for, it's part of the service. And then we're also continuously backing up these nodes. So query processing in Redshift. What happens is when you issue a query, it goes to the leader node where a SQL optimizer will do any logical transformations it can. It also keeps track of statistics on your system tables, cardinality of your columns, and it will build and pick what it thinks is the optimal query plan for your query. It will then generate and compile C++ code and then push that out to the compute nodes and execute it in parallel to get the result sets. And then we cache that compiled object code on the leader node so that we can reuse it if we see that query again. And that's an LRU cache of that compiled data. And typically, as long as the query execution plan doesn't change, you can use that same query with different parameters, for example, different date ranges, and we'll just be smart enough to reuse the code. On a data loading perspective, each node ideally is loaded in parallel, and this is what we recommend, that customers stage data on S3, or they can copy directly from DynamoDB. And recently at reInvent, we announced the ability to copy from any arbitrary SSH endpoint. And this can be done in parallel. So when you issue a single SQL copy, Redshift by default will load each compute node in parallel and will automatically distribute your data across the nodes. And if you think about a multi-node system where essentially we're trying to operate in parallel for query processing, thinking about distribution is actually an important thing. You want even distribution of data on your nodes so that you don't have hotspotting. But another factor that comes into play is if you have a schema with a lot of joins, then you might want to think about co-locating data that's frequently joined together on the same node so we don't have to ship data between nodes when you're running complex queries with lots of joins. And Redshift abstracts away a lot of this, the physical aspects of data layout for you. So you just define your tables using SQL DDL, and then we will take care of data distribution. You do have the option to specify a sort key, which I talked about for zone maps, and a distribution key, which will allow you to co-locate data. And so achieving that balance between even distribution and co-located joins is one of the goals of the system here. Data loading is done in parallel, and if you add more nodes, you'll get more parallel throughput. So essentially, you can have linear gains in load throughput based on the network connectivity between the nodes and your data loading source. And that copy from SSH capability is it's a fairly atomic piece of functionality that will let you copy directly in parallel from a MongoDB database or from SQL Server on-premise, or another very common use case for that is copying directly from HDFS clusters. So you can set up your HDFS systems and your nodes to accept SSH connections, and then run a Redshift copy, and it will copy in parallel directly out of your HDFS or EMR cluster without requiring you to put data onto S3. Backup and restore is done continuously as well in Redshift, and so what happens is anytime data is written, it's automatically replicated, and then it kicks off a continuous backup process in Redshift. And so that data is taken to S3. You can pick your retention period. By default, it's 1 day, but you can have up to 35 days stored in S3. You get free S3 storage up to the amount of data warehouse space you have provisioned. So if you're running a 10 terabyte cluster, you'll get 10 terabytes of free S3 backups. And the backups are incremental, so if only 1% of your data is changed after a load, then the new backup will only use 1% of the space, because we'll just add the blocks that have changed and keep track of what we need to do to restore state to any particular snapshot. You can also take a snapshot at any point on demand with a button click or an API call, and this will leverage any blocks already in the system, and that is never deleted until you choose to do so. And we, at reInvent as well, announced the ability to have your snapshots taken to a second AWS region. So if, for example, you're running out of US East and you wanted a copy of your snapshots in US West, you can enable that. It'll be done continuously. You pick your retention period on that side for those snapshots. And Redshift provisioning time is 3 minutes. So if your data availability time for a region outage is over 3 minutes, that's a perfectly valid availability strategy for you to use. And because we have a feature called streaming restore, which is the ability to essentially start querying as soon as the cluster's been provisioned and system metadata is loaded. We then spool in data from S3 in the background to respond to queries. Your time to availability is very short. And because you see that most users tend to operate on localized data sets, for example, at AWS, when we're looking at our data warehouse, we care a lot about the last day and the last week and the last month, and we occasionally care about the year and the year before that. And when you have multiple users accessing that same sort of temporal locality of data, that data gets brought back quickly to the cluster, and most users see normal performance once just a subset of the data has come back from S3. And that same streaming restore applies if a node fails and it has to be replaced. You can start querying as soon as that cluster is available because we're re-replicating data in the background from other drives where those copies are stored. Resizing Redshift is a push-button operation, something that's much, much easier to do in the cloud than it is on-premise. It's not, what happens is you push a button in the console or make an API call. You choose the type and number of nodes that you want, and you can resize up or down in Redshift. And what we do is provision a new cluster in the background, put your source cluster into read-only mode, and then do a parallel node-to-node copy from source to target. And the reason the parallel copy is important is we don't want cluster size to be the limiting step around resize times. It's really a function of how much data per node is there on the smaller of the source of the target cluster. So in this example, say you had 4 terabytes per node on the source system, so 12T of data, and you're going to a 4-node system, that will have 3 terabytes of data per node. So it's the rate at which we can move 4 terabytes off a single node. That'll be the rate limiting step for your resize operation, since all of that's happening in parallel. And you're obviously only charged for a single cluster, and when you're done, what we'll do is move your SQL endpoint to point to the new cluster, so you don't have to make any application changes. You can then resume using read writes and go from there. And if you don't want to be in a situation where you might be in read-only mode for several hours while this resize is taking place, what you can do is combine our snapshot and resize capability to clone a cluster from a snapshot, resize that clone, load any data that was generated in that interim period, and then point your applications to the new cluster. And so you can resize without any production impact, depending on your requirements from an application perspective. So we talked about a lot of techniques that we use for performance, and we really wanted to make this affordable. We wanted to price Redshift at a level that let you analyze all of your data. So you don't have to throw away data to fit within some free terabyte cap limit. It's really designed to be simple pricing. We don't charge you for the leader node, and we want you to know what you get. And so you can see we have our on-demand pricing model, which is our hourly pricing. And this is for the small node in each of the families. It's linear for the magnetics, and it's slightly different from linear for the SSDs. But essentially, the hourly rate for 2 terabytes of Redshift magnetic is 85 cents an hour. And that works out to $3,700 per terabyte per year. And if you use a 1-year reserved model, this is a commitment for a year, that drops your price by about 40% to just over $2K per terabyte per year. And the 3-year model brings that to $999 per terabyte per year. One of my colleagues was speaking at a partners conference, and someone came up to him and said, "Oh, surely you mean per month?" And no, it's in fact an annual price for everything on the Redshift side. And then on the SSDs, as we talked about, it's a smaller single unit. So this is 25 cents per hour for the 160 gigs of SSDs. And again, similar discounts with the 1-year and the 3-year model. And again, that 5.5x increase in cost on the 3-year model, 10 to 15x increase in performance. And you can see if you're running the 3-year reserved model, your effective cost on that single node is 10 cents an hour. And then finally, ease of use has also been something that's really important to us. And so provisioning is minutes, not months. We wanted to put a lot of information into the console to allow you to monitor your query performance, to look at the explain plans of queries, to figure out how to make them run faster, to see what's being executed, resize functionality, capability to secure your cluster, all of that's in the web console. Again, an area that we're always iterating in and always looking to make better. And I want to talk a little bit about Redshift security model. This is also something that we're proud of in the service. We build on AWS's already very rich security infrastructure. And with Redshift, you can really run completely secure and encrypted end-to-end. And so what I mean by that is you can load data onto S3 using client-side encryption. So that data is encrypted. You can load data into Redshift encrypted using the SQL copy. That data will be loaded over SSL connections. You can choose to enable encryption at rest in Redshift. This is transparent. It's AES 256. We use hardware acceleration to minimize the performance hit. Our tests show about 20% performance penalties. And all the data in your cluster is encrypted. So that means data that's stored, temporary spills to disk, all of your backups. And you have the choice of either letting AWS manage your encryption keys, or you can use an on-premise or our Cloud HSM hardware security module, so you can have complete control of encryption keys for your data at rest. And then you can require SSL for encryption of data over the wire. And so your entire chain can be secure. And that's allowed us to work with customers like NASDAQ, who have very, very stringent security and protection requirements. And they have a fraud analytics use case that they're using Redshift for. And so that's the encryption end-to-end story. And then in addition to that, you can also choose to run inside of Amazon Virtual Private Cloud, or VPC. And this is a part of the cloud where you can control the routing, the isolation, and you can hook it up to your data centers using VPN. So a ton of control over how your cluster is accessed. And in addition, all of the compute nodes live inside a private VPC, and so there's no direct access to them. They're completely walled off from the outside world. So your only interaction with your cluster is through a SQL endpoint, and there's numerous layers of protection around it. In addition to all of this protection, we also provide very fine-grained auditing. So you can use AWS identity and access management down to the resource level, so you can control which user can do what operation on what element in your system, whether it's a cluster or a snapshot. And all of that can be logged through AWS CloudTrail and have those secure logs on S3. And then we also enable database level permissions, so pick users, pick what SQL they can access, which tables they can use. And all of those queries, data loads, successful logins, and failed logins are also logged to S3 on secure locations that you can then consume for auditing purposes. And we're always trying to be ahead of our customers' requirements from a security perspective. So if you see things here that you wish, or you don't see things here that you want to see, please find me after the session. I'd love to hear about them. And Redshift is a managed service. And so what this means is that we are trying to take away all of the muck associated with managing a data warehouse and provisioning it, patching it, securing it, scaling it, so that you can focus on your applications and driving business value for your end customers. And so we have automatic replication of data within the cluster. This is to different drives on different nodes. This is to be able to transparently handle drive failure. If you think about it, if you're running a 100-node DW1 8 extra large system with 24 spindles per node, that's 2,400 spinning disks in your cluster. Just probability dictates that you will see a drive failure. We don't want your cluster to have a problem because of that. So we will handle it automatically. We will rebuild a copy of that data on different drives. That's why we have twice the amount of space free on those nodes. We're doing continuous backups to S3, which is designed for 11 nines of durability. You've got multi-region backup capability. And snapshots can be restored to different availability zones within a single region. And if you enable multi-region snapshots, you can restore to a second AWS region, giving you global disaster recovery capability. So while we're excited about the service so far, and Andy mentioned in his keynote, it's the fastest growing service at AWS really in our history, we're also very cognizant that we need to continuously improve the service. And so we've delivered over 50 pieces of functionality to Redshift since we launched. And really, it's all driven by customer feedback. And we like to have very close collaborative relationships with our customers. I'm speaking to customers every day, and we really want to hear from you if you are using Redshift and you see things that need to be improved. And none of you will be able to read this, but this is just to give you a sense of our roadmap delivery, what we've been doing from a feature perspective. We launched the service on Valentine's Day in 2013, just over a year ago. And as you can see, our feature velocity is steadily increasing. And I think that's true of AWS as a whole. And I have 3 new things that we really released last night, so you may not know about them. One is a direct copy from JSON. So you can have JSON files on S3 and do a direct ingestion into Redshift. Previously, you'd have to do some transformation or load those JSON fields into varchar columns and then use extractors to pull out the data that you want. Another piece of functionality that customers have been asking us for is regex substrings. So you can pull out substrings, use this in where clauses, things like URL parsing or extracting domain names from emails, string matching, really common use cases for us, especially in that area where customers are combining log data with transactional data. And then this is one that's, it's a really small feature, but I think it's really important around ease of use, which is a Resize progress indicator. And this is one where, if any of you here have resized your cluster, you were probably wondering how long it would take to complete. And so this has come into the console, and there's an API which will tell you exactly how far in the process you are. And I think the message here is that really no improvement is too small. We really want to hear from customers about what they're doing. And so speaking of hearing from customers, I'm going to turn it over now to Jay, who will talk to you about Redshift at Pinterest. So thank you very much.
So hi, everyone. I'm Jay. I worked on data infrastructure at Pinterest. So I've been working closely with Rahul to enable Redshift as part of the infrastructure at Pinterest. So now we have more than 100 terabytes data in it. We have more than 100 users using it regularly, and it's been an amazing experience so far. So I'd like to be here, share our experience. Because previously, I worked a lot with those big data systems like Hadoop, MapReduce, Hive, Pig. I also contribute to Apache Pig itself. But after coming back to Redshift, which is not open source but commercial, I was amazed by how much you can do, and so I really want to share our success with you. So first, as you may know, Pinterest, we help people to discover things you love and collect things. So we are one of the largest websites in terms of the traffic. We have tens of millions of users. We have tens of billions of pings. So we have a lot of data to analyze. So we track a lot of data in order to build a better product. So just a couple of use cases. For example, we use data to measure our KPI. We use data to run a lot of experiments to make sure our products work as we expect. So we also use all the data to build a recommendation to suggest you the best pins you may like. And there are some other use cases like fighting with spams and do planning for the new products. And all these are backed by all the data we tracked and this data infrastructure. So this is a quick overview of the infrastructure early last year. So first, we run everything on AWS. So we don't host any physical machine in our company. And that's one reason we can manage a very small operational team. And pretty much it's very standard infrastructure nowadays. We use Kafka as the general logging system, and we dump whatever data we have on MySQL, HBase, Redis to S3, which is our offline data store, and it's unlimited data size. And from there, we use the Hadoop MapReduce systems like Hive cascading to build our batch data pipeline, which includes our daily reports, which includes the recommendation engine. So that works pretty well because Hadoop, the MapReduce, was designed for this batch processing. But on the other hand, there's something that didn't work very well around the time. So first, the interactive data analysis was not doing very well because the only option we had at that time was Hive. So Hive is an SQL interface on top of the Hadoop MapReduce. And because MapReduce is not designed for low latency, Hive just performs very slow. So if you want to interact with Hive, you run a query, you wait for tens of minutes or a few hours, and then you run another query. You can imagine it's not efficient at all. So that's the first issue we had. And the second issue is because Hive has high latency, we couldn't use it as the backend of our analytic dashboard. So we use one single MySQL box, and you can imagine it ran out of capacity very quickly. So we quickly realized we need a low latency data warehouse. So what options do we have? So first, Hadoop is very popular right now. Pretty much many people use Hadoop. So people keep building more things on top of Hadoop in order to address the new problems. So we have SQL Hadoop like Shark, Impala, or Presto. These are all open source. They are very cool systems, and they are fun to work with. But we found at this point, they were still immature for us, so we couldn't afford the engineering resources to support these systems. So we also have the massive parallel processing, the MPP systems. We have Vertica, Extradata, Paraxel. So these systems are built on top of Postgres, which is a 20 years old technology, so it's very mature. But these are expensive software, so we couldn't afford it. So finally, we have Amazon Redshift. It's built on top of Paraxel, so it's mature, it's powerful, MPP. But because of the AWS, the on-demand model, it's also cost-effective. And since we also run everything on AWS, so it makes sense for us to use Redshift. So Rahul gave a great overview of all these highlights, but I will just quickly review this in the perspective of customer. So first, the on-demand model really allows us to quickly test the software technology and in different configurations, cluster sizes, hardware, to figure out if it really works for us. And we don't need to wait for our finance team to approve this budget. And once we feel confident with this technology, then we went and bought this 3-year reserve instance. And the price was transparent. Everybody got the same discount, so we feel great. And also we got a free snapshot. We got backup on S3. And the second highlight I want to mention is the extremely low maintenance overhead. So with clicking a button, you got a cluster set up, running, and you don't need to worry about the hardware, software, the network, different configurations, because it's all pre-configured with the templates that's built by the experts. So we don't have a dedicated DBA at all. With one engineer, pretty much it can cover everything we need. So we have automated maintenance and upgrades. So new features just keep coming without any human intervention. And it has a great built-in administration dashboard. So it covers pretty much all the core health metrics. And you don't need to add additional metrics by yourselves. And the final highlight pretty much is the most important highlight of Redshift is the superior performance. So we did our own benchmarks with our own data, our own queries, and we compared with our own Hive cluster, and we found Redshift can easily achieve up to 100x performance against Hive. So there are a couple of reasons of the performance. So first, Redshift has extremely efficient columnar data format. But in Hive, we have all kinds of data. We have JSON, Thrift. Even the RC file in Hive is not as performant as Redshift columnar format at all. And also, Redshift has a great query engine. It collects all kinds of system stats in order to build the best query plan. But Hive doesn't have that. But having said that, so you don't need to trust this benchmark. And I would suggest you run your own benchmark with your own data and your own query and compare with your own other system, because that's what the number you really get. So you may also see some other benchmarks on the internet, and I feel like it's very hard to do an apple-to-apple comparison of different systems because the performance can be affected by so many factors. And that's why when we did the benchmark, we didn't tune each system. We just used them as they were. And we found that Redshift just gave the super performance out of the box. So how do we implement Redshift? So having said that, Redshift is much faster than Hive. It doesn't mean that we need to replace Hive with Redshift, because they are meant for different use cases. And in fact, if you don't have Redshift yet, you probably have already used Hadoop and Hive already. And you probably don't want to replace it. And also, if you do want to use Redshift, you probably still need Hadoop and Hive to prepare the data, clean the data in order to copy to Redshift. And that's exactly the same for us. So we use Hadoop and Hive for a couple of years, and all of our data is in Hadoop and Hive. So first thing we need to do is to build the ETL to copy the data in Hadoop and Hive in order into Redshift. So unlike Hadoop, which is very flexible, it can process all types of data, including JSON, Thrift, all kinds of data, text, but Redshift requires specific formats of data so that it can build a very efficient columnar data format. So we use Hadoop and Hive to extract data out of Hive itself and transform into a format that Redshift can process onto S3 as the staging area, and from there we copy to Redshift. So a catch of this pipeline is S3 is eventually consistent, especially in the US standard, which means if you write some file to S3, it may not immediately be available to read. So we were very lucky to hit this issue very early. We just found that some of the data just got missed in Redshift because we just copied the data too quickly. So after playing with this, we figured out if we can reduce the number of files on S3 by merging small files, which is a very common problem in Hadoop, we could achieve much lower consistency issue on S3. And also, of course, we need to have the audit process to measure how much if we lose any data at each step. And also, and the Redshift team also just released a new feature so that you can have Redshift just wait for a couple of files to be available on S3. But this is something you need to be aware of. So we did spend a lot of time to figure out the best scalable way and reliable way to set up ETL. It's the hardest part. So here's some quick best practice. So first, we need to schematize the Hive table, right? So what we did is we just write some scripts and generate the ETL query and do this heavy lifting transformation. And we also clean a lot of data that's dirty so that we don't run into any problem when loading the data to Redshift. But after data is ready, then there may be some other issue to load data into Redshift. So for example, if you try to load a big table in one shot, then Redshift will try to build some index for the data. It may take very long. So we figure out we can just do the heavy sorting in Hadoop itself. So we sort it in Hadoop, we make it ready, and then we load data in chunks to Redshift. So Redshift doesn't need to do all the heavy work. And also, if you have a lot of tables in time series, then you copy the data day by day, and if the data is sorted by the date in Redshift, then you don't need to do a expensive vacuum operation to make sure the table is sorted, but it's already sorted automatically, like Rahul mentioned earlier. And at the end of the ETL, we need to do some table retention because Redshift has limited disk storage. So we found that if you are familiar with a traditional database, then you delete some data, you need to do a vacuum to really release a disk space. But we found that that was really expensive in Redshift. So instead of deleting the data in place, we just create a new table with a subset of the original data. And that works very well for us. Yeah, so hopefully you're not stressed out by this because this is a little, tedious. So after we got data, is it ready for the superior performance? So the answer is almost yes. Yes, so unlike those Hadoop Hive systems, there are hundreds of parameters to tune. I did it a lot, and I didn't enjoy that. Redshift just gives you the best performance out of box. And if you really want to understand the performance, there are only two things you care about. First is it's based on Postgres, so it has a system stats. So you need to make sure whenever you update the database, you need to make sure that system stats is up to date because it's used by the query optimizer to generate a query plan. So if the stats is outdated, then the optimizer will generate some crazy plan that make the performance very worse. And the second thing is pretty much Redshift doesn't have configuration other than letting you specify the sort key and disk key of the table. So sort key means the table is sorted by this column, while disk key means the table is distributed. So sort key will speed up the filters, so you can skip the data, and the disk key will speed up the joins. So if your query is slow, then you need to make sure you are utilizing the sort key and disk key. But that is all. So having said that, if you don't follow those two things, you may run into some performance problems like we did in our early days. So we did do a lot of performance debugging, and I'm sure Redshift team is doing great support, so they are always ready to help you to debug the performance problem. But it's still worth doing your own homework because you may run thousands of queries a day, and you don't want to, you don't want to rely on them to help you on all the cases. So we found that we found the explain command is extremely useful for us to understand the performance issues, and it's very simple. It just shows you how exactly Redshift execute a query. So for example, in our early days, we had a case that the query just took 3 hours to run. And after looking at all the states, and we found we just didn't update the system stats. So what happens there was we did a join between a big table and a small table, and Redshift assumes the big table was smaller, so it replicates the big table to other machines in order to join the small table. And the big table was more than 10 terabytes, so you can assume how slow it could be. But fortunately, it did finish successfully, so you can also imagine like how reliable Redshift is. Unlike some SQL Hadoop systems, they can easily run out of memory, get failures if you don't write your queries carefully. So the next thing is, so you understand the performance, you also need to educate your users to help them to write efficient SQL queries. So for example, Redshift is columnar database, right? So you need to tell users to take advantage of this to select only the columns you need instead of select all the columns, which they used to do in Hive, because in Hive, they don't care about the latency at all. So when they start using Redshift, when they realize their query is slow, they keep just coming to us and complain, and we need to explain them. You need to understand Redshift a little bit and using it the right way. And for the other case, Redshift has done a great documentation, so you can find most of this best practice in the standard Redshift documentation. So Redshift is a shared service, so half of our companies, more than 100 people, are using it regularly. So you can imagine they are sometimes competing with each other. So you can imagine one person run a big query that just occupy all the resources so that other users just suffer from this particular user. So that happens quite a lot because Redshift is getting widely adopted inside Pinterest. So more and more users heard about Redshift, and then they tried out Redshift without reading our best practices. So that's some issue we addressed. So instead of letting the users come and complain to us, we set up some proactive monitorings. So Redshift does a great job to keep track of all the query information inside of the system tables. So we can just query these tables to get some runtime information of who are running what kind of queries right now and how long they have been running. So using this information, we could monitor these slow queries. And before the users realize, we reach out to the users and tell them, hey, your query is slow and you may make some mistakes. You should read our best practice first. Also, at the end of the day, we analyze the pattern of the daily queries and find what kind of queries are slow or top 10 queries so that we can reach out to the users, educate them better. But still, we run into this contention problem. Some big query occupy the whole cluster. So we really spent some time working on this. And first thing we did is we schedule those heavy ETL queries, like the copy queries, copy data from S3 to Redshift. Those are very resource intensive, and you don't want to run them while users are using Redshift. So we have a very strict schedule for these queries. They could only run in the midnight. And if they couldn't, we delay those ETL queries. So we make the trade-off. The data may not be immediately available in Redshift, but our users always get the best performance. And the second thing is, during the peak hours, during a day from 9 a.m. to 5 p.m. when hundreds of users are using Redshift, we have to time out the user queries. So currently we time out all the queries longer than 20 minutes. So what they can do is either they go check the best practice, optimize their queries, or they wait until after 5 p.m. And it's surprising that it works pretty well. No user complained to us because half of the time they just have some typos in the queries, and those queries are super crazy. And another half of the time, those queries are just essentially very expensive. They are just over the limit of the hardware, couldn't finish in 20 minutes. So they are willing to wait after 5 p.m. So with these two tricks, we managed to solve the contention problem, and pretty much everybody's happy right now. So here's some statistics of the Redshift usage at Pinterest today. So you can see we tried out a different setup of cluster, and we settled on 16-node cluster with up to 256 terabytes of size. And we copied about more than 2 terabytes data per day. And you can imagine we'll run out of capacity very soon. So what we did is we have a retention setup for those biggest tables, because we observed that users may not need the table, may not need the old data. And right now we have more than 100 regular users, and they ran more than 500 interactive queries per day. And among those queries, 75% of them finish between under 30 seconds. So you can imagine that's amazing if you use Hive or Hadoop before. And 90% of them are less than 2 minutes. So this is extremely good result. And finally, I want to highlight that the operational effort we spend is really, really small. So we spend less than 5 hours a week to support all things related to Redshift, including maintaining the ETL pipeline, including supporting the users, the software, the system issues, because Redshift handles most of this automatically. So I was lucky that this was my first project. I spent full time about 3 to 4 months setting this up. But after that, it just worked very well. So I was able to switch to another project for full time while maintaining Redshift just as a side project. So this is updated data infrastructure. So you can see Redshift has been integrated as part of this. And now the interactive data analysis has been working very well. And as the next step, we are going to integrate Redshift with our new analytics dashboard so that we can power more powerful analysis. So finally, I want to just say thank you to Rahul's team. It's my first project at Pinterest. It's been extremely successful so far. So that's really impossible without this great technology. So I know there's no perfect things, but to me, Redshift really seems perfect, bug-free, and they provide timely support. They work closely with us to help us get there, and they are always open to the new feature request. So this is something I really want to help. I really want to share our success with you so that more people can realize this great technology can take advantage of that. Yeah, so that's it. So thank you.